Picture this. It's 3 a.m. The plant floor is eerily quiet, and that's not a good thing because your main production line just slammed to a total halt. You walk up to the control panel, and there it is, a flashing red light on your variable frequency drive and a completely dead motor. Look, it's an incredibly stressful moment. It doesn't matter if you're a first-week apprentice or a 20-year veteran automation engineer, you're losing thousands of dollars a minute, and the drive is just staring at you, spitting out some cryptic 3-letter code. Well, welcome to this explainer. Today, we're going to take that exact panic-inducing situation and transform it from a total mystery into a moment of absolute mastery. We are diving deep into the diagnostics and troubleshooting of the Altivar machine ATV320.
Here's our quick roadmap for this explainer. We'll start with the theory of drive diagnostics, move into decoding the parameter menus, do a hands-on tutorial, break down a real-world night shift case study, and wrap up with the golden rules of resetting. Let's jump in.
All right, part 1, the theory behind drive diagnostics.
Before we start mashing any buttons, we really need to understand what the ATV320 is actually doing when things go wrong. Inside this drive is a microprocessor, and it's constantly monitoring everything: voltage, current, temperature, comms, the whole shebang. When it detects something weird, it doesn't just randomly stop, it logs the issue right into its internal memory. It is actively trying to tell you what went wrong. And it communicates these problems in 3 main ways. First up, we've got alarms, or warnings. Think of this exactly like your car's check engine light. The motor keeps spinning, production is running, but you definitely need to investigate. Second, we have faults, which we commonly call trips. Now, this is like your car's engine deliberately stalling out to prevent a catastrophic blowout. The drive actually cuts power to protect your equipment. And finally, third, we have configuration errors. This just means the drive has been programmed with conflicting parameters and literally cannot start until the math is fixed.
Moving right along to part 2. Let's decode those fault menus.
Now that we've got the theory down, let's learn the actual parameter language you need to talk to that internal computer. Your main command center here is the FLT- or Fault Management menu. Before making any changes, you'd typically check the parameter, which just shows you the very last fault that popped up. From there, you've got RSF, which is Fault Reset Assign. Out of the box, this defaults to NO, but you can actually assign this to a digital input. That allows an operator to just push a physical button on the outside of a panel to acknowledge and clear a fault, assuming, of course, the physical problem is actually fixed. Next is ATR, the Auto Fault Reset. This tells the drive if it should try to automatically restart itself after a trip. If you do turn ATR on, you then have to look at TAR, the Fault Reset Time, which tells the drive how long it should keep trying to pull off that auto restart. And finally, RFLT, Clear Error History. This wipes the slate totally clean. Just a heads up though, to even see RFLT, your drive's access level usually needs to be bumped up to expert mode.
Actually, hold up a second. I need to shift gears and get super serious for a minute. When you crack open the manual for the ATV320, right under that ATR, Auto Fault Reset parameter we just talked about, there is a massive, incredibly strict safety warning. It says, "Warning, unanticipated equipment operation." Look, if you enable Auto Fault Reset and the cause of the error just magically disappears, the device is going to automatically resume normal operation. Think about the reality of that for a second. If an operator has their hands in a machine trying to clear a jam on a conveyor belt, and the drive decides to auto-reset right at that exact moment, that motor is going to instantly start spinning. The manual explicitly states that failing to follow these instructions can result in death, serious injury, or major equipment damage. So, the rule is simple. Never, ever use auto reset on applications where sudden movement poses a safety risk to your personnel. Period.
Okay, let's get into part 3, a quick, hands-on troubleshooting tutorial. Time to put our hands on the hardware. Now, if you're lucky enough to be using the remote display terminal option, which is usually mounted right on the outside of the electrical cabinet door, you don't even have to open up the high voltage panel to do your diagnostics. It's great. Check out the physical interface. You've got a bright 4-digit display. You have the mode key, which is your toggle to cycle between reference, monitoring, and configuration menus. But the absolute VIP here is the jog dial right in the center. It acts as your enter key, marked ENT. You just rotate that dial to scroll through your menus and push it straight in like a button to select a parameter or lock in a value.
You know, to truly master diagnostics, you really should know how to deliberately trigger faults in a controlled environment. It's the best way to test your setup. For example, to simulate an SLF1, which is a Modbus communication interruption, you can quite literally just unplug the network cable from the drive. Bam, fault triggered.
To test a USF or supply mains undervoltage, you can drop the incoming voltage threshold on a testing bench. And to trigger an OCF, an overcurrent fault, you can artificially drop the motor's current limit parameter down below its normal operating draw. By forcing these faults intentionally, you get to safely watch exactly how that 4-digit display reacts, so you aren't surprised when it happens for real.
So, how do we actually clear the drive out once the physical issue is fixed? Here's your exact 4-step sequence. Step 1, press that jog dial, the ENT button, to access the CO and F menu, then go to the full menu, and scroll your way down to the FLT- menu. Step 2, once you're in there, read the triggered fault code. Let's say it's USF for undervoltage. Step 3, to properly clear out the error history and get a fresh start, you have to make sure your access level, that's the LAC parameter, is set to expert. That's the secret to unhiding those advanced options. Step 4, scroll down to RFLT, press Enter, turn your dial to flip it from NO to Yes, and press Enter one last time. The drive clears its memory, and you are officially ready to command a restart.
Which brings us perfectly to part 4, our case study, the night shift crisis.
Let's put all this theory to the ultimate test in a high-stakes scenario. We're back to 3 a.m. Our night shift technician gets a frantic call on the radio. The main cooling pump drive has tripped, and production is dead in the water. The tech grabs their tools, speed walks up to the cabinet, and sees the hardware. The ATV320 main unit is tucked safely inside the cabinet, but that remote display terminal on the door is flashing a bright, angry red error.
Now, a rookie operator might totally panic here, or worse, they might just start mashing buttons trying to force the system to run. But not our tech. They don't even touch the main power switch. Instead, they look right at that flashing display. It's flashing USF. Thanks to their training, they know instantly this means supply mains under voltage. Think about this. The drive didn't fail, the pump didn't jam, the drive actually did its job flawlessly. A massive storm cell is rolling over the factory right now, and there was a temporary dip in the city's power grid. The drive sensed that voltage drop and tripped on purpose to protect the pump's motor windings from frying.
So the crucial step now is resolution. The tech checks the facility meters and verifies that the grid power is bounced back to a rock-solid 480 volts. And the manual states clearly, for manual resets, if the cause of the error disappears, the device can resume normal operation. Since the storm passed and the voltage is good, the root cause has officially disappeared. The tech uses the remote terminal, dives into the fault menu just like we practiced, executes the manual reset to wipe the USF fault, and hits the run command. The pump spins right back up, smooth as silk, and the whole factory is back online in under 10 minutes. They saved the shift simply because they understood the diagnostics.
All right, let's wrap this up with part 5, the key takeaways and the absolute rules of resetting.
Whether you're an apprentice who's just learning the ropes or a seasoned engineer designing a brand new line, there are some foundational rules you absolutely have to respect. First off, know the difference between an alarm, which means go investigate, and a protective trip, which means the drive just saved your very expensive equipment. Second, get really comfortable navigating that FL- menu so you can properly configure fault resets using the RSF and ATR parameters. Third, and I cannot stress this enough, always respect those unanticipated operation safety warnings when you're automating a reset. And finally, the single most detrimental mistake you can possibly make, never, ever blind power cycle a trip drive. Seriously, do not just walk up to the main disconnect switch and yank it off and on hoping the problem magically goes away. When you do that, you force a hard reset that totally wipes out the immediate context and clears the drive's active memory. You are literally destroying your own best diagnostic data.
So, I'm going to leave you with this final, provocative thought to take back to the plant floor. The ATV320 is an incredibly intelligent piece of hardware, and it is trying its absolute hardest to tell you exactly how to fix your process. So, what critical diagnostic data are you destroying the next time you instinctively reach for that main power switch instead of just reading the display? Respect the drive's intelligence, read the fault, and turn that mystery into mastery. Thanks so much for joining me on this explainer. See you next time.